who's a theoretical physicist working at VU University and thinking about quantum stuff. And he'll talk today about a state-averaged quantum algorithm for an equal footing description of ground and excited states on a near-term quantum computer. So Saad, please go ahead.
Okay, thank you for the nice introduction. So indeed, we have been developing a quantum algorithm recently dedicated to NISQ devices in order to solve a problem. Actually, our motivation was to describe accurately conical intersections thanks to a NISQ algorithm, an hybrid quantum classical algorithm. So the purpose of this talk will be to introduce the concepts. And in this talk, actually, I will take time in the first part to introduce and do the connection between quantum chemistry and quantum computing, but I know that most of you are used to this right now. In the second part, I will give the motivation why actually conical intersections are important in quantum chemistry, and also why it is actually pretty difficult to represent conical intersections already on a classical computer. And in the last part, I will introduce the approach we have developed. And we will give an application of a small toy model that is called format that contains a conical intersection. So here we go. So all of you know that's one of the most promising problems we try to solve with quantum computers right now. And more precisely in the NISQ era is the electronic structure problem. So we are interested in solving the Schrödinger equation, describing the arrangement of the electrons around the nuclei in the molecule. And getting access to a ground state or a first excited state is pretty important because it encodes a lot of important information regarding the chemical affinity between species and all that kind of stuff. So what we try to solve here is a quantum many-body problem, pretty difficult. And most of the time what we do on a classical computer is that instead of working in a first quantization approach, contrary to what Ryan Babouche demonstrated earlier, we most of the time try to treat this problem in a second quantization form. So I will stick to the second quantization form from now on. And in this case, the very first step is to treat the Hamiltonian and reshape the problem in a mean field approach. So what we do is we do a cheap mean field calculation just to build some electronic modes that are called the molecular orbitals, in which we are going to put the fermions to build up in a given basis set. So a basis set formed by atomic orbitals. We are trying to build linear combination of this atomic orbitals to build this molecular orbitals. And we use this as the second quantization basis in which we put all the fermions, and we try to actually build an exact representation of the ground state within this basis set by building all the possible electronic configurations, so all the possible slated determinants. So as you know, this approach is pretty good if you are dealing with small system with small basis sets, but it scales dramatically with the size of the system. And this is precisely where we expect quantum computer to shine, because it requires an exponentially lower amount of unit of information to encode such a wave function. And what we do on a quantum computer in the NISQ era is that we make the assumption that each quantum wire, and more precisely, each qubit is going to encode the occupancy of a given spin orbitals. For example, for the hydrogen molecule in the minimal basis set, we only need 4 qubits. And what we do with that is we manipulate the state of the qubits. So for example, I can just flip 2 of them, and at the end of this very short circuits, I build the first most important determinant, that is the Arthur-Fock determinants. But most of the time, we try to go beyond that naturally, and we use I would say in the NISQ era, the very famous variational quantum Hilbert solver that all of you know. And what we do is we improve this initial slated determinant by applying a unitary transformation on top of it, depending on a lot of gates with given parameters. And the shape of this unitary is most of the time motivated by the type of problem we're trying to solve. So if we are dealing with quantum chemistry, we can take advantage of some knowledge we have from this field. And now it seems to be a very common approach to use the unitary couple cluster by including some double and single excitation inside this unitary. Translating this into a qubit form and implemented it is a well-known fact now by the concatenation of some C-note gates and some rotations. And what we do is then we use this unitary there as a unitary transformation to actually reshape this, transform this initial state into a more complex one, a correlated wave function. And in the variational quantum Hilbert solver, we use that as an ansatz state So on one side, we have the quantum processor. On the other one, we have the classical processor. We are interested in solving a given problem, for example, the hydrogen molecule. And the job of the classical processor is to provide a set of theta parameters, so to wisely tune the gate, so that at the end we have an ansatz that we can, for which we can measure the associated energy. So we do a sampling here, and we measure the electronic structure Hamiltonian average over this trial states. And based on the knowledge of the sampling, we can then again wisely tune the parameter gates in order to minimize the associated energy. And thanks to the variational principle, we know that the lower the energy is, the better it is, because the ground state represents the lower limit of our energy. So if we're interested in a ground state, that's the way we do that until we reach convergence. And as an example, if you apply that for this very small system, that is the H2 molecule, I give in green the results with VQE, and in red the reference, the full CI approach, exact diagonalization in the minimal basis. We have most of the time pretty good matching. So that's it for VQE, I would say. Why VQE is so interesting, actually? Because in the NISQ era, VQE is recognized as the most promising approach. It's requiring short depth circuits, and also it should work with shorter amounts of qubits. However, there are some problems with this, because if you want to treat some very important and practical quantum chemistry problem, I mean, larger ones or problems that are actually containing some strange features, such as very complex degeneratives, well, most of the time what we do is we use the active space approximation. And this approximation can be most of the time a problem, because what we do is that in this active space approximation, we use quantum circuits with a reduced amount of qubits in order to treat the problem only within a given active space. And when you invoke such an active space approximation, it may be that in some cases you totally miss very important information that should be actually present in your system. And if you are restricted to calculation only within an active space, actually you are missing the point. And that's what I would say most of the VQA calculation would lead to. So just to give an illustration of this, I'm going to show that the active space approximation can be a problem when, for example, you are trying to describe conical intersections. So what is a conical intersection? That's actually a single point of degeneracy that connects two potential energy surfaces. So here, for example, a ground state in red and a first excited state in blue. And why is it so important? Because in quantum chemistry, conical intersections are playing a key role in many photoinduced processes, such as, for example, photoisomerization, but also photodissociation. So let's take a look at it. In this first case, photoisomerization, you have initially a molecular system in its cis conformation located in a pocket of its ground state, so at room temperature. But when a photon strikes your molecule there, the electronic wave function can get promoted to its first excited state, and as the shape of the first excited state space is not a local minimum, most of the time your molecule will move will move over the surface thanks to non-radiative relaxation, and can finally go through the conical intersection present here. And it may be possible that either it goes in its initial state, but also it can go in another local pocket. And you can end up with a new type, a new configuration for your molecule. That is here a trans conformation. So you are really seeing here an isomerization that is mediated by the presence of a conical intersection in the spectrum. And you have also similar type of process with photodissociation. You start with two bounded fragments, and a photon comes and strikes your molecules, and your two bounded fragments can end up totally photodissociated. So at this step, I hope that you're convinced that conical intersections are pretty important in quantum chemistry. That's also a problem that actually has been mentioned a lot this week, if I remember correctly, by even. So this is a pretty common feature, but in quantum chemistry, it is also a well-known fact that trying to accurately describe that kind of spectral feature is actually complex, most precisely when you're dealing with active space approximation. And this is precisely what I'm going to illustrate right now with a toy model, a that is the formaldimine molecule, so small model, but rich enough because it contains the conical intersection. And I just remind briefly what we assume when we do the active space approximation. It means that you think about all your wave function, ground state, first excited states, and so on, as the following. You assume that the shape is always described by three different subspaces. The first one that is a frozen occupied molecular subspace, always double occupied. Another one where you put and you can play with all the possible electronic configuration, called the active space. And the last one where you assume that there is never any electrons, called the virtual one, frozen virtual one, or unoccupied ones. If you do this approximation and you try to catch the conical intersection of this molecule, in blue, I represent what you obtain with a very large active space. So it's almost a full CI calculation. Everything is done here in the CCPVDZ basis. And I focus on the plane where phi is equal to 90 degrees. And I simply vary here the landing angle. In blue, you have this, I would say, very accurate calculation. And as you can see, we can catch here the crossing between the ground state and the first excited state. We have the conical intersection that is present here. However, if you reduce the size of the active space, such as you only focus on 3 molecular orbitals with 4 electrons inside, you have the result in red. And what we show here is that we totally miss the information. We are not able to accurately represent the conical intersections. And we could not then try to study around the conical intersection the very complex photoisomerization process, for example. So in other words, if you only stick to small active spaces, in this case, you totally miss the point, and you totally miss the important parts of the chemistry that is present in your system. So that will be the error that VQE should do actually also, if we restrict the VQE to a small active space. So what can we do in order to solve this problem? Well, there is also another very famous method that is not the CASI one, but the state-averaged CASSCF approach. And if I do a state-averaged calculation with exactly the same active space, the same number of electrons inside, and so on, I can actually retrieve this very interesting feature just present here. And what is new actually with this state-averaged CASSCF? Well, it's a well-known method in quantum chemistry. I would say classical quantum chemistry, classical treatment of the wave function. In this case, the only thing that changes is that you treat your all your states in a state average way, and you try to minimize their energy always in a state average way. And the new tool is the orbital relaxation or orbital optimization approach there. And what you do is that you allow some rotations between your orbitals, between the different subspaces. And when you do that, actually, it's a new degree of freedom to minimize even more the state average energy of your wave functions. And what you're able to do is to catch a lot of static correlation that is present outside the active space. So everything happens is here as if you were able to catch a lot of information from outside the active space. And thanks to that, you are able to catch this important feature that is the conical intersection. So that was for us the main motivation to develop actually a quantum algorithm for the NISQ era based on that kind of approach with a VQE approach. So we wanted to extend that to a VQE approach. So I'm going to now introduce the state-averaged orbital optimized VQE approach we've introduced. But before doing that, I would like to say that we are really standing on the shoulders of giant, because all this work is also very inspired from a lot of work that is already present in the community and very recently. So I can, for example, cite the Nakanishi paper where they introduced the subspace search approach dedicated to solve the electronic structure problem and find multiple electronic states simultaneously. But also, I would like to put some lights on these 3 papers from Mizukami, Sokolov, and Takeshita, who have been actually already put some efforts in combining the concept of orbital optimization with VQE. But in this work, the thing was that the authors mainly spent time on demonstrating that you can do that for a single state, for the ground state. Okay, but in our case, what we want to do is to extend all of this to accurately and treat always on an equal footing, accurately describe on an equal footing multiple states, and to mimic the state average KCCF, but on a quantum computer. So here is the flowchart about the quantum algorithm. In the first step, what we do is we realize the state average VQE. So we use two orthogonal initial states. We have necessarily the Hamiltonian associated to the molecule we want to solve, for which we want to solve the electron structure problem. We switch to the active space representation. So it means that we build a frozen core approximation Hamiltonian, and we use this Hamiltonian as the operator on which we are doing the measure. And what we do is we use a unique quantum circuits with a unique unitary employed in order to transform both initial states into two correlated states that will be used as two ansatz to catch the ground state and the first excited state of a molecule, for example, for diamine molecule. And what we do here is that we minimize the state average energy associated to these two states. So you do that again and again, and at the end of this state average VQE, you end up with optimal correlated states that should span exactly the subspace of the ground states and the first excited states of this Hamiltonian. Okay, and based on the knowledge of the states, more precisely their respective 1 and 2 RDMs, we give the 1 and 2 RDMs to an external classical state average orbital optimizer. And the role of this state average orbital optimizer is to reshape the molecular orbitals of the system in order to minimize the state average energy of your two states. Simultaneously, you treat on an equal footing, once again, your two states. And the idea here is to introduce this orbital rotation operator, whose actually has the shape, whose shape is the exactly equivalent to the unitary couple cluster with only single excitation. So here, just for you to know, this exponential minus kappa is more or less equivalent to this single excitation version, unitary approach. And we use that to transform the Hamiltonian. And we go back to the frozen core approximation, so to the active space approximation. And based on this new degree of freedom, the kappa parameter, so the linear combination of all the molecular orbitals within a given space, inside and outside the active space, we minimize even more the state average energy. And we do that in a loop. We can solve that very efficiently with well-known algorithms, such as the Newton-Raphson algorithm, similar to what is done in KCCF, actually. And once this is done and it reaches convergence, we end up with an optimal transform frozen core Hamiltonian that we give back to the state average VQE. And at this point, the state average VQE takes over, and it tries once again to find the ground state and the first excited state of this new algorithm, of this new Hamiltonian. And you do that again and again, this macroscopic loop, and also the internal loops, until the whole SAOO VQE algorithm reaches convergence. And this is what we can obtain out of it. So I take the formal diamine molecule as our toy model. First of all, I would like to give some precision about the initial state we consider. So we use the Hartree-Fock-Slater determinant and a singlet excited version of the Hartree-Fock determinant. And the orbital optimization we are realizing is over the first 20 molecular orbitals. And I focus only on the variation of the alpha parameter there. So this is precisely what is occurring when you do the calculation over the whole path without any orbital optimization. Actually, it's pretty encouraging already, because it means that that state average VQE is able to reproduce CAS-CI calculation. So it does the same mistake. We are not able to catch this conical intersection. But then if we introduce the state average orbital energy and we do this alternance between SAVQE and SAOO parts, this is what we obtain. You have the state average energy in black, and you have the reference, the KCCF reference energies in dashed lines. And a white strip represents here SAVQE phase, and gray strip state average orbital optimization. And as you can see here, after just a few SAO VQE cycle, we reach convergence, and we match the state average KCCF energy. If you do that over the whole path there, you can end up with a pretty accurate representation of the conical intersections if you compare that to this state average KCCF reference. So we end up here with somehow a quantum analog for NISQ era of the state average KCCF algorithm, the classical algorithm. So this is very, very encouraging. And if you go beyond simply representing the passes, what you have is also the fidelity of the state. So here we computed the fidelity with respect to some reference states that are the state average KCCF states. And what we observe is that if you do this SAO VQA approach, actually you end up with a fidelity that is always higher than 99.75%. So it means that the states are also encoding the same physics there. So it's also pretty encouraging if you want to use the states, for example, to then study the dynamics around the conical intersection and all that kind of stuff. And finally, the last thing, if you are interested in the photo-induced process in itself, you may also be interested in the difference of energy. And I represent here this difference of energy. And I compare that to state average KCCF, but also to this almost full CI calculation with a very large active space. And what you can see here is that indeed we also, we once again here match perfectly the state average KCCF results. And we make some error compared to this almost exact diagonalization simulation. But there, well, we think that if you then simply extend a little bit the active space, you will finally end up with a similar representation of the conical intersections. So, long story short, with all this simulations, we were pretty happy about that because it means that we managed to find a way to mimic state average KCCF with a VQE approach. And what are the perspectives right now for this approach and for all this work? Actually, what we would like to do is to extend this quantum algorithm to quantum dynamics. We would like to study, for example, all this very interesting process in quantum chemistry that are this relaxation through conical intersections. But also another very interesting point I'm currently investigating with my colleagues is the exploiting this quantum algorithm in order to actually automatically detect conical intersection in the parameter space, which is also something that we believe is important for quantum chemistry. So at this point, I would like to thank you for your attention. If you're interested in the paper, please check it. It has been recently published in Quantum Science and Technology under this name. And now, if you have any question, I will be really happy to answer and discuss with you.
So thank you very much, Saad. Let's all thank Saad again. I think we don't applaud, but you can imagine it. And right, so let's go through the questions. Do people have questions for starters? Any questions? Because I had a few. No, then everyone's fine. Could I go ahead? So you have these two initial states, and I was wondering, as the first question is like, how free are you in your choice of those initial states, and how much does that choice actually? How would that influence the actual overall performance of the algorithm? So I guess if you completely choose something completely crazy as the other initial state, then I don't know, what is the intuition there of how which two states to choose?
So first, I would say that we chose these states because they are actually the simplest one. If you want to stick to a subspace, or at least expect to stick to a subspace that is first preserving the spin symmetry, we are working in a single. We want to end up with wave functions that are preserving the symmetry. So this is why we use the Hartree-Fock states and the singlet excitation version. What I can say then concerning the choice of the states is that I also tried that in some simulation. Instead of using this, I simply use a doubly excited version of the Hartree-Fock determinant. It's always a state that is of spin symmetry, a singlet one. And what I observed is that we should end up with a similar result, but it takes more time. It takes more SAO VQE cycles. So there it will be like a little bit longer. And sometimes also a little bit less accurate, but that's also a problem that can maybe be solved with a better classical optimization, I guess. So long story short, these two states were pretty good to finally represent the subspace. in catching actually the interesting physics. But if you simply choose like a little bit more different states, yeah, the counterpart is simply that it takes longer, I guess.
Okay, thanks. Does anybody else have questions? More questions? Okay, then maybe one more. So you said in your flowchart, you said those two states that you choose as initial state, they're sort of correlated. And I'd sort of, in which sense are they correlated? So if you look at the energy function that you prepare, it looks like you're looking at sort of in the classical mixture between those states. So like a density matrix on those two states. In which sense, like, can you explain how, in which sense they're correlated?
Do you mean there's two initial states?
Yes, exactly. You say optimal correlated states. That's I was a bit wondered. What do you mean?
Okay, so when you say classical mixture, for me it's not that clear, because it means that you somehow lose the quantumness of the states. Do you mean that you're could you be just a little bit more precise concerning this feature when you say?
Right. No, I'm just trying to understand what you meant by optimally correlated in that setting.
So simply it means, in other words, it means that this should be the ground state and this should be the first excited state. And the word correlated is, I guess, stemming from the usual lingo from quantum chemistry, when you say that you catch some electronic correlation inside a complex wave function, more complex than simply a single determinant. So it's a linear combination of determinants.
Gotcha. Thanks a lot. There's one more question in the Slack channel. And so Nathan Fitzpatrick is asking, do you have any idea how you will approach a variational algorithm for non-adiabatic dynamic state crossing through the conical intersection, as you said in your last slide? The nuclear degrees of freedom are quite troublesome. Yeah,
that's true. No, that's true. That's a fair point. That's a complex question to answer. But well, that's something we still have to investigate. But maybe some ideas we could also have is to mix different type of quantum computers. I guess, and by this I mean that we can, for example, expect to. I hope I'm not wrong when I say that, but we can, for example, try to solve the electronic parts of the problem, the electronic wave function on a qubit device, and try to solve the nuclei parts on a continuous variable quantum device, so with photons. So that maybe could be an approach to solve this. But yeah, so far that's a question we have to dig more, I guess.
Okay. I guess we're probably up for the yes. So let's thank the speaker again, and virtual applause, and thanks a lot.